Hello, you are welcome to today's class on number systems. Today we have a question on hexadecimal, the octal, and then the binary, and then also the decimal. So we have a question: convert the hexadecimal number, that is A2DF. We have to convert it to binary. After that, we convert it to octal, and after that, we convert it to decimal. So how do we go about that? So let's quickly begin. Okay, so there are several ways we can solve this question, and the way I would like to use today is I'll first of all convert the hexadecimal to binary, because it's much simpler when we do it that way. But anyway, there are so many ways. We can convert this to binary, then we can convert it from binary to either octal or the decimal, and that's very fine. So I want to convert this to binary. So if we have A2DF, hexadecimal means that it is represented in base 16. So in base 16, we do not write 16, okay? Now, A represents 10, okay? A represents 10, B is 11, C is 12, D is 13, E is 14, and then F is 15. So any number that is in the hexadecimal form, when you see A, it represents 10. D represents 13. F represents 15. Okay, good. So it means that the number we have here is 10. This number is 2. This one, D is 13. And then F is 15. Good. Now, what we just have to do is that we have to convert these numbers to base 2. Yes, that's binary. So we want to convert 10 to base 2. How do we convert 10 to base 2? So there's this table we can write. So we have 1, 2, 3, 4. Sorry, it's 1, 2. 1, 2. Here must be 4, 8. You just keep multiplying by 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. Good, so when we take 10, how can we add the numbers here to have 10? You know, to get 10, we need to add 8 to 2, right? 8 plus 2 gives us 10. So 1, 1, then you just fix zeros. When you get the answer for this, the rest of the other spaces, you replace them with 0. So 8 plus 2 is 10. We didn't use this space, we didn't use this, so we replace them with 0. Now, when we take 2, 2 alone can give us 2, so we just write it like this. Now, when we take 13, to obtain 13, we can add 8 to 2, and then we add 8, yes, 8 plus. So you can rather do it this way. 8 plus 4, that is 12, then plus 1. So here will be 0. Okay, and then the last number is 15. So 15, we can, yes, 8 plus 4 plus 2 plus 1 is 15. So 1, 1, 1, 1. Okay, so we've converted the numbers from base 10 to base 2. So 10 in base 2 is 10, 10. Okay, 1, 0, 1, 0, then we write a subscript of 2. 1, 0, 1, 0, 2. So this is the equivalence of 10. Then 2 is 1, 0, base 2. 13 is 1, 1, 0, 1, base 2. 15 is 1, 1, 1, 1, base 2. Good. So in binary, the answer for A2DF in binary is going to be, let me explain this. The A we have, now the reason why we use only 4 numbers, we can use more than 4 numbers to represent 10. If we want to use 6 numbers to represent 10, we just need to add 0. We just need to keep adding zeros. Okay? But then the reason why we are using 4 numbers alone is because we are working in base 16. The number that has been given to us is in base 16. And 16 is written as 2 exponent 4. So it means that we have to represent each digit here using 4 numbers or 4 digits. to be more technical, we say we use 4 bits to represent the numbers. Okay, so we use 4 bits of 4 digits to represent 10, 4 digits to represent 2, 4 digits to represent 13, 4 digits to represent 15. So you see that the 2 is 1, 0 base 2. Okay, this 2, if you want to represent it in binary, it is 1, 0 base 2. But because we want to use 4 numbers to represent them, we have to add 0, we have to include 0, 0. But it doesn't still change the value of the number. Okay, so the A was first, and A is 1, 0, 1, 0. Then the B is 0, 0, 1, 0. That's the 2. And then the D is 13. So 13 is 1, 1, 0, 1. And then 15 is F, and F is 1, 1, 1, 1. So that is it. So A2DF in binary, it is 1, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1. That's how we write it. So I want to plane this table so that I can use the space here, okay? Good. Okay, so we have to convert this from binary to octal. So if you want to convert this from binary to octal, it is very simple. The only thing we'll do is that, you know, octal means you are working in base 8, or octal means that convert this which is in base 2 to base 8. So we want to convert it to base 8. The 8 is the same as 2 exponent 3. The 3 means that we have to break this binary into 3 parts each, 3 parts each. So we take the first 3 numbers, 1, 2, 3, we bring this division, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Good. We are even supposed to bring another 0 and 0 here, but it will still not change the meaning. Then now what we'll do is that we subject the digits here to exponents of 1, 2, 4, the same way we do the 1, 2, 4 there. 1, 2, 4, 1, 2, 4, 1, 2, 4, 1, 2, 4. So the only thing we'll do is that we'll multiply 1 by the 1 at the top. So 1 times 1 is 1, plus 2 times 1 is 2, 4 times 1 is 4, so plus this plus 4. So 4 plus 2 plus 1 is 7, so we have our 7 here. Now we also do same, 2 times 1 is 2, 1 times 1, so we have 3 here. 1 times 1 is 1, 2 times 1 is 2, so we get 3. Here will be 1, here will give us 2, and then here will give us 1. So it means that the answer we are getting is 1, 2, 1, 3, 3, 7. Sorry. 1, 2, 1, 3, 3, 7 base 8. 1, 2, 1, 3, 3, 7 base 8. So it means that the equivalence of the binary we had here is 1 in base 8 is 1, 2, 1, 3, 3, 7. Okay? So I would like to write that here. Okay, so this is 1, 2, 1, 3, 3, 7. Now we have to do the same. We now have to go and convert to base 10. The decimal here means that we are converting it to base 10. Okay, good. So how do we convert this to base 10? How do we do that? Okay, so the only thing we have to do is that we need to write. So we have 1, 2, 4. I'm coming. Okay, so we have 16. We multiply 16 by 2. We have 32. Times 2 is 64. Times 2 is 128. Times 2 is 256, I guess. Times 2 is 512. Times 2 is 1024. Times 2 is 2048. Times 2 is let me do that. So that's 4096. Times 2 is 8192. Times 2 is 16384. So some will ask why am I writing a very longer table? So the reason is that we have to fix these numbers in the table. So let's fix the numbers in the table from here. So we have 1, 1, 1, 1, 1. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. That's here. So we have 0, 1, 1, 0. 0, 1, 1, 0. That is up to this side. So we have 1, 1, 2, 3. So 1, 2, 3. That's up to this side. Then we have 1, 0. So it's left with the last one. That is 32, 7, 6, 8. 32, 7, 6, 8. Okay, so the only thing we'll do is that we'll multiply 1 by this, 1 by 2, 1 by 4, 1 by 8, 1 by this. Then the answers we get, we sum the answers. When we sum them, the answer we get will be the value in base 10. Okay, so you have your calculator, you can do that as I'm also doing mine here. Then we compare and see whether we are going to have the same answer. So I'm adding 32, 764, sorry, 32, 768, 32, 768. Okay, so after summing all of the numbers up, I had 41695. So this is in base